Hello all, welcome to week 7 of our deep learning tutorial sessions. So let us wait for a few more people to join and then we can start. In the meantime, so this time we covered topics related to bias variance trade-off, and we also saw how different regularization techniques can be enforced in the deep learning setting. So if you have any doubts for this week or any of the previous week, you can discuss it here. Or if you would like to go over any concept, we can also discuss them. Okay, so I guess no more people will be joining. So yeah, so just the first topic that was discussed this week was on bias variance trade-off. So uh, have all of you got to the what is the trade-off? What is the actual significance of bias or variance? Or should I go over it? So you can unmute yourself and ask if you have any doubts, or you can just write it down in the chat and I will try to explain that.
So, like, it's just for doubts or the topics will be explained?
Yeah, so if you have any doubts regarding any topic, I can describe those here. Or if you have any other doubts regarding previous assignment questions or previous topics, you can discuss that here. So you must have gone through the videos of this week, right? Which is about bias and variance and the trade-off and different regularization schemes, or mostly the L2 regularization scheme. So if you have any doubts regarding that, you can ask, because someone has to ask, right? Because this is a doubt clearing session, so I'll try to I'll try to clarify your doubts. So is there anyone who has taken, I mean, I assume you must have taken the machine learning course, right? Either in NPTEL or some other course. So if you have taken a machine learning course, then the concepts on bias and variance must be familiar to you. Is there anyone who has not come out, who is not familiar with, or who is still not clear about what is bias and what is the trade-off that we talk about? What is the meaning of overfitting, underfitting? Because whenever you are whenever you are dealing with practical neural networks or practical data, you will always face this issue of overfitting. So basically, what you have to do is you have to select the model with the best validation loss, and so to select a model with the best validation loss, and that is where this you want that your test loss is not does not degrade over time. So that is how where you don't want your model to overfit only to the training error. So since none of you is asking any question, let me share my screen and scribble down something.
I want to know about underfitting. Like overfitting is
Okay.
clear to me. Like in
Mhm.
overfitting, like it's overlearning by the model. What's underfitting?
Okay, sure. Good. Let me share my screen. My screen is visible, right? Uh, Please hold on. There is some issue here. Ah, so underfitting, right? So basically, before understanding underfitting, we actually have to know what is fit, right? So what is fitting exactly? You are given some inputs x1, say you are given n inputs, and I say this is my set x, and corresponding to each input, you have the outputs. So you have y1 and you have yn, and this is my output set y. And the goal of any machine learning algorithm, be it a neural network or be it some other algorithm like logistic regression, linear regression, or any other algorithm, the goal is to learn the function f, right? Learn f such that f of x is equal to y. So here f is your true function. F is your true function. So this is easy to show via drawing a figure, and I'll show an example for a regression. I think such an example was also shown in the weekly lecture. So suppose you have some points like this, and let us say these are one-dimensional points, and this is your x-axis. So that means you have some data set with only one feature, right? And this is your label. And now I ask you, what sort of a function should will output this? So let me say that this is say one, this is 1. This is say what is some 2. So I'm just guessing. So this is say 2 is something like 1.5. This may be 3, and this is maybe 3 comma 1.1. This is 4. 4 is again 1.6, and we have some 5, and this is something say 1.2. Right now we wanted we want some function f such that f1 is 1, f of 2 is 1.5, f of 3 is 1.1, and so on. And we want to learn f. So our question is, what is f, right? So f is our true function. So if you have some easy numbers, say I say f of 1 is say 2, f of 2 is say 4, and f of 3 is 6, f of 4 is 8, and suppose I give you this, say I give you inputs 1, 2, 3, 4, and their labels are 2, 4, 6, 8. So your input output set is something like this, say 1 comma 2, 2 comma 4, 3 comma 6, and 4 comma 8. So in this case, what is f in this case? Can anybody say this? What is f in this case? What do you think f can be? So get the question, right? You are given this given this data set where your point 1 has a label 2, point 2 has a label 4, point 3 has a label 6, point 4 has a label 8. So can you come up with some function which, when I give this x as input, it gives me this? What is a possible value for f here? This is easy, right? So is the question clear? Can anybody speak up? Hello. Am I audible? Hello. Okay, so you get the question, right? So I give you a data set where your where your features are 1, 2, 3, and 4, and your labels are 2, 4, 6, 8. So what can you say f is? What is a possible f? What is some function that is f of 1 gives 2, f of 2 gives 4? So what can this function f be? Right. So there's 2x, right? It's a simple function. So it's a functions is 2x. So for this data set, uh, we see that our function is this quantity 2x. So this is our true function, right? So whenever we are given this data set, we just see what is the input, what is the output, and try to learn this. This is a true function. We try to learn some approximation of this. We may not learn 2x. We may learn something like 1.9x. We may learn something like 2.2x. We may not be. It may not be possible to learn 2x. So it depends, because whenever we are doing gradient descent, suppose we are doing gradient descent and we initialize the parameters in such a way that the randomness lets us gets us gives us some noise. So now if I give some function, say f1 is 1, f2 is 4, f3 is, or let it be 8, f3 is 27, f4 is 64. So what is f in this case? Yeah, it's x cubed, right? So that means if I say that my data set has x which are greater than equal to 0, so that means this is my x-axis, this is my y-axis. So you have 1 1 2 8 327 464, so on. So you have some curve like this, right? So you have some curve like this, right? So this is your fx equal to x cube. Now suppose this is a true function, and now suppose I have a neural network, and suppose my neural network is, say, some, it outputs some function f8. So this is my function learned by a neural network. So as I said, this is an easy function, so it may very well learn this, that x is equal to x cube. But suppose we do not learn the exact function, we learn some function, and suppose my neural network learns some function which is, say, uh, like this, right? Or you have, so suppose this is the case. So now if we look at this, the loss, what is the loss? So loss is basically at each point what is the difference between this blue curve and this red curve, blue curve and this red curve, blue curve and this red curve, right? So in this case we see that as x increases, so in this direction our x increases, the loss becomes more and more, right? So that means we are not able to get a good fit. So ideally we wanted to, so in the ideal case I wanted to learn a function something like this, something close to this, but maybe due to SDD or due to some randomness in training the neural network, we are only able to learn something like this. So this is not a good approximation, or this is not a good approximation to the true function. So this is my f hat, and this f hat minus f, it is large. So if it is large, it means that it is not able to feed properly to the data. So by feed, I mean if I am able to learn the exact curve, so we say that it is fitting the data. But here I am not able to feed properly to the data, so I am underfitting. So this is a case of underfitting, right? Because if you are not able to unable to feed to the training data, so if you are unable to feed to the training data, what does it say about the train loss? So is the train loss high or is the training loss low? Anybody? What is the training loss say?
Training loss is low.
Training loss is high, right? So you want this, so it is large, right? So for 5 we'll have something like 125, and this will be here. So we have a large training loss, right? Because you are not able to fit properly to the data. If you are able to fit properly to the data, you'd learn a function something like this, say like this curve, right? So
So
this is
then training loss will be high in both overfitting and in underfitting. In both it will be high, na? Training loss.
no for overfitting the training. So we'll go to overfitting after this, and I'll show you. I'll give the indication why it will be low. But for underfitting, you are not able to feed properly, so you are unable to feed properly to the training data. So training loss in this case will be high because you wanted to learn this function, but you are still have this much of loss, right? So this is high. So is this clear? So again, if we relate back to what was taught during this week's lecture, if our training loss is high, so what can you say about the bias of this model? What is the bias we have? Is it high? Is it low in this case? So this much is clear, right? Why I am saying that the training loss is high, or uh, is there something that is not clear?
This much is clear.
Yeah, right. So in that case, when our training loss is high, what can we say about the bias of this model that we have learned? Is it high? Is it low? So remember, bias is basically your true function minus the uh, this function, true function minus the learned function. So if training loss is high, what is loss basically? So loss is basically the difference between the true function minus your uh, minus the learned function, right? That is loss. That is the loss. So now I'm talking about the training loss, and I am saying that the training loss is high. So that means this quantity is high. This is a true function. This is the learned function. I am saying that this is high, and if this quantity is high, that means your bias is high. This is clear, right?
Yes.
Yeah, right. So now let us look at another case. So suppose you have some function like this. So you have some function, say, again, I give you certain points. I give you this point, this point, and this point. And I ask you to, and I say that the true function is something like suppose the true function is a sine wave. Yeah, my drawing is not okay, but something like this. So suppose it is a sine wave. Suppose f, this is x, and f is equal to sine of x. Or rather than sine, let us say it is some polynomial, say some like x to the maybe 10 plus some quantities, right? And you have some like something like this. So I give you some points. So suppose I give you 4 points, and on 4 points my function looks something like this. About this, sorry, so this is a true function, right? So I know that my function looks something like this, and I give you 4 points. And suppose I say that my function f that I want to learn. Suppose give I try to learn a linear regression for it. So if I learn something, so if I learn a linear regression model for it, as it goes to x values, then the loss will be low. Then up to what parameter we can consider is low or high. So you mean as we go closer to the y values, right? So these are the y values. So as we go closer to the y values, so it uh, depends, right? So in this example, my loss is high because so even though for some earlier samples, so even though for some earlier samples, I'm getting these losses to be low, but this will grow something like this, and so it will grow something like this. So the loss will be very high, right? So by low or high, it is just a matter of how you interpret as low or high. So in this case, suppose your losses are of the, it depends. So suppose, for example, the losses are of this form, right? Say 100, 200, 300, and suddenly if I get a loss of 15,000, so this is a high loss with respect to the other ones, right? So it depends on what type of uh, interpretation you're doing. So basically, if we know that uh, my function is like this, and your outputs are, so your outputs will be along this line. So suppose at 5 you have 125, and here you'll only get some 30 or something like this. So it is a huge loss. But for some other case it may be small. So it depends on what type of problem you are looking at. So there is no parameters low or high. So this is just a conceptual thing. Like we want the losses to be low, and by losses to be low, we mean that we want the function that we learned, that is fn, to be as close to uh, f as possible. So if we got something like this, say, so we have this, and compared to this, if we have something like this, so this is a better function that is learned than this one, right? So why do I say that this is better? Because the losses are low in this case, the losses are high in this case. So I will prefer this model because this has lower loss than this model. So is that clear? Okay. Hmm. So yeah, so suppose my true function is, so suppose for this example, my true function is like a 10-degree polynomial. And now I say that I am learning a linear regression model. So if you're not familiar with linear regression, that is basically saying we are learning some parameter w, and given some input x, you multiply it with some this. So again, so this is basically a line, right? This is something of the form y equal to mx plus say 0. So the function or say f that will be learned will be a line. So given these samples, so I'll mark this in black. So it will try to learn some, say, line something like this. So suppose this is the f that is learned, and this f is basically your w transpose x. So now, what do you think? Is this a good fit for the data? Is this a bad fit for the data? So how we can say whether it's a good fit or bad fit? Suppose I give a new test point. So suppose my test point is this one, right? Suppose this is my test point. So even though uh, for this point the loss is okay, this is a okay loss, but given a test loss, this is high, right? So this is high. Even for training loss, I want this to be large, but this is large. Again, these things are large. So compared to some other model, compared to the true model, so we have some large training errors here. So again, is this linear regression a case of overfitting or underfitting based on the previous discussion? Is this linear regression model overfitting to the data, or is it underfitting to the data? we have not gone to overfitting, but okay, is this a good model or is it a bad model? Yeah, this is underfitting, right? Because you have large error. So this is a large error. This may be this is a bad model. So how do we decide that this is a bad model? Because we see that these losses are large. These training losses are large, right? So that means it has a high bias, right? So this is a high bias. This is underfitting, and yeah, so this is high bias and underfitting. Now instead of this, suppose again I take this points. Now let me draw it here. So suppose now I take a different set of points, right? Suppose I keep a point here. So we're talking about the same model, same function f, but I'm taking different points. So something here, something here, something here, something like this. And also there is some point here, say, right? And now if I say that so this is a noise, like this is a noise. Why I'm saying that this is a noisy data? Because we know that suppose we know that our points lie only on our function or only on this curve, but this is a noisy observation. So by noisy I mean you made some error in the measurement. So suppose you are what are you doing? So yeah, so suppose you are looking at images of monkeys, and somehow you see an image of a cat. So the image of a cat is not actually part of the data set, but that was there by some mistake. So that means there was some noise that you saw. Suppose these are your monkeys and this is your image of a cat. Right? And now suppose, so now I know that my model is a 10-degree polynomial. So suppose now I say that the model that I want to learn is say 50-degree polynomial, something like this, right? And now it will try to learn this data, right? So now what it will learn? It will learn something like this. It will, because it's a 50-degree polynomial, there will be a lot of curves here. So it will learn this model very closely, right? So now compared to the true model, this is a, so when I'm doing this, so now look at the training losses. So what are the training losses here? Anybody, what are the training losses in this example? Are the training losses good? Are the training losses bad? Uh, what do you mean by this statement? I'm not sure. So when I say the what, how good is your model? So how will you evaluate your model? Of course, we'll evaluate your model by the losses it has, right? So if some, so like I saw that for this example, if we consider a linear model, it has high losses, high training losses. But now suppose I consider model which is say a polynomial of degree 50, so then it will try to learn all of these points. Yes, so because I am saying that my polynomial or my function is a polynomial of degree 50, it will, so how does a 50-degree polynomial look like? A 50-degree polynomial will have a lot of these many terms, right? So basically it can learn a lot of curvy information, right? So a polynomial of degree 2 is something like this, a polynomial of degree 3 is something like this, degree 4 is something like this. So as you increase your degree of polynomial, your the curviness, if we want to use some loose term curviness, it is also, it becomes more zigzag. So if I use a high degree polynomial in this case, so it will try to learn everything, even the noise itself, right? So in this case, what are the training losses? Are the training losses good in this case? Are the training losses bad?
Low. Training loss is low.
Yeah, training loss is low, right? So training loss, you can say it is almost zero in this case, almost zero. So we have, so if the training losses are zero, what happens to bias? Is the bias high? Is the bias low? So remember, bias, again, going back to the definition of bias, bias is basically expectation of f minus f, right? Yeah, right. This is low, right? Because this thing is low, so our bias is also low. So now let us say consider the same function again, and now I will change the points because we are looking at the same function, but we are looking at different points of the function. So suppose I take these points. Black. So what was our assumption? Our assumption was that so we are assuming that we want to learn some function which is a polynomial of degree 50. So because again it is a degree 50 polynomial, it will try to learn all of these points. Again, you will get something like this. Right? Again, in this case, our training losses are almost zero. So almost zero. That means we have low bias, right? So now for convenience, so let us say that this is our first sample of data. This is sample one. And for say I say that the function learned here is f1. And suppose this is my sample two. So we are taking the data set. So we have say 100 points and I am taking 10 points, 10 samples at different time and learning a function with only these 10 points. So suppose this is my sample two and I say that my function, this is my function two. Now, if you look at it, so are these function one and function two close? The learned function. So are these function, so is this quantity high or is this quantity low? So these are the two functions that we have. Are these two close to each other? So I'm not talking about a real function, the true function f. I'm just talking about a learned function. So for the first sample, you have f1 head. For the second sample, you have f2 head. So are these two functions same or are they similar? So what can you say about the quality of the learned function over the two samples? Do both of these sample learn the similar function, same function, or
No.
do they learn a different function? Yeah,
different.
yeah. They both of these are different, right? So f1 hat is not equal to f2 hat. So they learn different functions. So why is it so? So so see, because we are giving a very high degree polynomial, so we are saying that the function that we want to learn, it will try to learn almost all the curves in the all the points in the data, right? So that is why even though this point, so this was my noisy point. So even though this sample had a noisy point, it will also try to learn that point, and it will give us a some function something like this. But now if we don't have a noisy point here, we have some say normal good points, it will have a function something like this. So because we are giving a very high degree polynomial, it will try to memorize everything in the data. So this function is memorizing everything in sample one, and this function is memorizing everything in sample 2. So earlier we had the case where, so what was the case here, or here the case was that it was not trying to learn anything, or it was not able to learn anything, it was not fitting properly, it was underfitting, right? But here when I say that my function is a high degree polynomial, it is able to fit everything, whether that function belongs to the whether that function is close to the true function or not, it is able to learn everything. So here it is even able to learn some noisy data. Here it is able to learn all of this function properly. So basically it is not only fitting, it is overfitting. You get that, right? Because it is overfitting to even the noisy data, because if we wanted a good fit, we wanted to learn, we do not know this, but suppose we know that the data belongs to some function which is a 10-degree polynomial, and our true function should look something like this. But since while learning we are giving some information that it has to be a 50-degree polynomial, it is trying to overfit to the noisy data as well. You get that, right? This is overfitting. So again, is this concept of overfitting clear? So is overfitting clear? We saw that underfitting was when you're not able to fit anything close to the true function, but now it is able to learn anything that you give. So suppose you give it something, suppose you give something like this, it will learn a function something say like this, instead of learning the true function which is something like this. So no matter what the true function, it is overfitting to any noisy data that you may give, right? So that is why we say that it is overfitting to the data. So this is clear, right? So when we are saying overfitting, what do we see? If it is overfitting, that means the training losses are going to zero, right? So if the training losses are going to zero, what happens to bias? It is a low bias, right? Now, where does variance come in? So variance is basically the quality of function that we learn here is something like this. The quality of function that we learn here is something like this. And the example that I saw there, the quality of function is something like this. So based on the data, there is a variance, right? So there is, if we want to compare the three functions, so my first, so suppose I have something like this. My first function, first sample is giving me a function something like this. My second one is giving something like this. My third sample is giving a function something like this. So this is basically your f1 head. F, I don't know which one is this. This is f2 head, I think. Oh no, this is f2 head. This is f1 head. This is f3 head, say. So see, we are trying to learn the true function. My true function is something like this. So this is my true function. But based on different data, we have a high variance, right? So for one data set, we are getting a function this one. For another data set, we are getting some function this one, and the third one we are getting something like this. So that means there's a huge variance in whatever you're trying to learn, right? So whenever there is overfitting, right? Overfitting, so it implies that we have a high variance, right? And if it also implies that if we have a low bias. So, but if we are talking about, so now we are talking about high variance, fitting everything to the data. But if you are talking about underfitting, so will these underfitting models have high variance or low variance? What do you think? So why did we get this high variance? We are getting high variance because it was trying to learn everything in the data, which is overfitting. And because the data changes, our model that is learned also changes. So that means we have a high variance in the type of model that is learned. But now if I say that if we have some model that is underfitting, so that means it is not able to learn, or it is not able to fit properly to the data that is given. If we change the data, will the function change? Will the underfitting model change, or will it remain same? What do you think? So for this example, we are saying we get a line. If I change the points, we will still get a line, right? So will that line be better than this line, or will the slope of the line change? What do you think? So give me 2 minutes. Think about it. Yeah, hi, hello. So yeah, so you get my question, right? That if you have an underfitting model, it will not uh, try to learn everything about the data because it is not able to fit itself. So will there be a high variance in this case or will it be a low variance? So you understand the case of high variance, right? Why we are saying that it has a high variance? Because given the data, your type of function that is learned also changes. So that means it varies. It varies according to the data. But if your data is, if your model is underfitting, it does not matter what type of data you are getting. So even if you change the data, you will get a function. So even if you change the data, you'll get a function say something like this or something like this, but mostly in this set. So that means there is no variance. No variance in the sense that the type of data that you have, the type of sample that you have, it does not change your function drastically. So if you have underfitting, that means you have low variance. So if you have underfitting, you have high bias. High bias, that means you have large training loss or high training loss. And if you have underfitting, that means you have low variance. So this trade-off is clear, right? So this is your bias variance trade-off. So any doubts in this? Anything that is not clear? Okay, good. Mm, so now, so there is a very important curve, which are called learning curves. And if you are designing some, not only deep learning, if you are designing some machine learning algorithm in the future, this is a very important curve to look at because it will make it will help you make decisions on what hyperparameters to use. So you must have heard of hyperparameter tuning. You have heard of model selection. So this is where it will help. So suppose on the x-axis you have something called as model complexity. So model complexity is basically how complicated your model is. So again, answer me this. So I give you a model which is a linear regression. So which is this one. So linear regression is basically a straight line that you are learning. And I give you a polynomial, say 50-degree polynomial. So out of this, which one is the more complex model? The linear regression one, first one, or the second one, which is more complex?
Second one.
Yeah, the second one is more complex, right? Because it will try to learn something like this is a very complicated model. So in whenever you're looking at model complexity, so here your decisions come in. Like so uh, let me say how complicated your model is. So let me say if your model is linear regression, that means you have a polynomial of degree 1, you have a polynomial of degree 2, polynomial of degree 3. So line is basically a polynomial of degree 1, right? So x something like this, w transpose x is a polynomial of degree 1. So by degree 50 we mean that we have something like w50x 50, something of that sort. So this is not concretely true, but you get the intuition maybe. So suppose these are your degrees of the polynomial that you're trying to learn: 3, 4, 5, and say up to 10. So as we increase the degree of a polynomial, your model becomes more complex. So there are other notions of complexity. So for this example, since we are looking at curves of this type, I am just saying that suppose degrees determine our model complexity. And here I want to plot the error, right? So there are two types of error. We want to look at the training error and we want to look at the test error. So now, so out of, so here, this, so for this example, the second function that we were learning, this was a degree 50 polynomial, which is a highly complex model, and this is a simple model. This one is a simple model, which is a linear model. So as we increase the model, based on this, as we increase the model, what should be the training loss? So will it increase? Will it decrease? What do you think?
When we increase the model complexity, the training loss will be reduced.
Yeah, right. So training loss will be reduced, right? So now if I want to plot the training loss, so it will, so it will have some starting point and then it will reduce something like this, right? Good. So now let us look at bias variance in this case. So when my training loss is high, what do we have here? High bias, low bias. What is the bias here? My training loss is high. That means we are not, we are in the underfitting, we are in the underfitting part of the learning curve. So what is the bias in this case?
Underfitting means high bias.
High bias, right? Because we are not, we are getting a huge training loss. We are not able to learn anything properly with say degree simple model. So here we are at a high bias because our training loss is also high in this case, right? So we have a high bias here. So basically we are underfitting. So this much is clear, right? And now when I increase the model complexity, so I'm increasing the degree of the polynomial. So in this case, what is the bias here?
Low bias and
Yeah,
overfitting.
yeah, we are overfitting to the data, so this is a low bias, right? So this was a training loss curve, train curve. Now the important thing that comes. So basically whenever we're saying as test error or validation error will mean the same thing. So by training error we mean the error which we get on data that we have seen during training, and you have not seen some data, we can refer to it as a test loss or validation loss. So I'm using the term loosely. Basically validation is just for selecting a model and test loss is just the final loss that you get, but here I'm just using this term loosely. So now let me plot the test loss here. So when my model is simple, anywhere but test loss will be high, right? So as I increase the degree, as I increase the complexity of a model, it is observed that our test loss will also decrease. That is fine. We expect that to happen because we're still able to learn the true function, right? So our test loss will decrease. But after a certain point of time, we get into the overfitting regime. So by overfitting, we mean that so suppose our training data was something like this, right? Suppose this was our training data. So the loss is decreasing, the loss is getting to zero in this case, but the test point will not come from the test point will not be a noisy data, right? So you are looking at monkey images, you saw a cat image, which is noisy, but whenever you are looking at a test image, it will most probably be a monkey image because we're looking at only monkeys. So that is why we will get a test point here, we'll get a test point here, we'll get a test point here. So in this case we'll get a test point here, so maybe a test point here. So because it is overfitting to the noisy data, so after certain time the test loss will start to increase because the training loss was not a good sample. We learned a very bad function in that bad function in that case, bad function in the sense that it overfitted to training data, so training loss increase up after certain time. So it becomes something like this. So this is your train error. Oh, sorry, this is the test error, test or validation error. So this is clear, right? Why the test error may increase, or why the test error increases even though your training error decreases. So in the lectures, there is also some mathematical derivations which motivate this observation. So we can also go over those derivations. Those are very nicely explained. So yeah, so in this case, as our test error increases, so why does our test error increases? Because the function that we are learning on the sample is not it is overfitting to the training data. That means it is going to 0. So if it is overfitting to the training data, what happens to the variance? So in this case, what will be the variance? So it varies as we change the data. What will the variance in this case? High,
High
low?
variance.
Yeah,
High
right.
variance.
Yeah, right. So we have high variance here. So now look here. So this is what you observe, right? So whenever there is a high bias, so that means we have a large training error. We have a low variance. That means you're underfitting. But if you have a high variance, you're overfitting. You'll because you're overfitting, you'll have a low training loss. So if you have a low training loss, that means you have a low bias. So high variance and low bias. So these learning curves also show you the same thing. So how does it help? So these curves are clear, right? Because you will encounter these curves repeatedly whenever if you are trying to implement some function. So so what we want to select the model. So in this case we see that the model at the model which has a model complexity related to a polynomial of degree 5 is giving us a minimum test or a validation error, right? So you will say that this is the best model that we want to select. So suppose you have a choice of a lot of models. So based on these laws, you will say that the model that I want to select is the model you want to have something like f at is equal to x to the 5 plus something. So this is how you can use the training curve or learning curves for hyperparameter tuning and other model related decisions. So this much is clear, right?
Yes, sir.
Yeah, right. Okay. So now talking about model complexity, what other model complexities? So if you, so whenever we're talking about the gradient descent algorithm, so what is a gradient descent algorithm? So gradient descent algorithm is basically you have this for t is equal to 1, 2, 3. Say I want to run it for 1000 iterations. You have some W0, which is some random weight, random parameters. So basically I'm looking at gradient descent algorithm. So your WT plus 1 is WT, so it's W1. WT minus some learning rate. times the gradient. Suppose you're also given some loss, gradient of some loss with WT. So this is your gradient descent update. So basically you start at some weight, and basically you try to get close to the optimal weight as you increase the number of iterations. So basically you are learning more and more about, you are trying to learn a more complicated model in each case, because you are trying to decrease your training loss. So because you are trying to decrease your training loss, that means you are trying to feed properly to the data. That means you are learning a more complicated model. That is what we see, right? If your trading loss becomes lower and lower, you are trying to feed, and it may be a case when you get to a zero training error, that means you are overfitting. So in this case, model complexity, so if you are drawing these learning curves, so you can say that this model complexity is basically your number of iterations, and this is your error, right? And so as you increase the number of iterations, your training loss will go on decreasing, because gradient descent always converges, but your training loss may, sorry, the test or validation loss may show something of this sort. So this is, so that means you know that how, so suppose this lowest point comes at around, say, for example, 50 iterations. So what do? You store all of these weights, and you know that the weights that you get after 50 gradient descent iterations are the best weights. So you use only these weights for testing the model.
So what is a hyperparameter?
Right. So yeah, in this example, whenever you are talking about gradient descent, you look at this parameter, right? Eta. So eta is your learning rate. So this is a user defined learning rate. So these W's are, you give them randomly, but using this update rule, the W's are updated. You don't have to give these W's explicitly, except the first time. These uh, this gradient is also computed automatically, because it depends on the loss that you have as well as the parameters at point t. But what about this eta and even this number of iterations? So when I say parameters, these are the parameters, right? These W's are the parameters, because these things are what you are trying to learn so as to get to the true function. But these things, this eta, t, these will, these are not actually directly related to the type of true function you want to learn. These are just some user defined variables, that inputs that like. So these are your hyperparameters. You understand, right?
Okay.
What is the difference between, yeah?
Yes.
And because this is a user defined hyperparameter, so a user can give anything, right? Like for this example, the user may have
Like
said,
generally also wherever we take eta or
hmm,
error as that epsilon or
huh,
gamma or anything like that, all those are hyperparameters.
yeah, right. Those are hyperparameters. And because the user will not know anything in advance, you'll have to try out with a lot of hyperparameters. Like for this example here, so this loss curve, I'm trying the hyperparameter t. I don't know what is t, so I run the algorithm for say t equal to 1000 iterations. And I observed that when my t is 50, we get the minimum loss. So that means I tune my hyperparameter that I want to run only for 50 epochs, 50 iterations. I don't want to look at the later iteration. So this is an example of hyperparameter tuning. So even for learning rate, say suppose you will have a learning rate of say 0 0.1, 0 0.01, 0 0.001, and so on. So if I want to tune according to this uh, learning rate. So this tuning part is clear, right? So next, the thing that was discussed was regularization. So before going to regularization, actually, yeah, let me say what is regularization. So when we are looking at these learning curves, so you saw that as we increase the model complexity, you begin to overfit and your training loss degrades, right? Your training loss increases. We don't want that to happen. That means we don't want very highly complicated model. We want to look at only simple models, right? We want our models to be simple. So regularization is a technique which says that, or which prevents your data from uh, going to more complicated model regimes. You just want your model to be some simple model. So that is the regularization. So before going further, I'm assuming you know what the L2 norm is. Can anyone say, so suppose, sorry, suppose I give you an give you a factor 3, 4, 5. So you may be aware of this, but I'm still looking at it. 3, 4, 5. What is the L2 norm of x in this case? The square of this maybe.
Yeah,
Anyone?
can you explain L1 norm and L2 norm once?
Okay, sure, sure. So suppose I have a I have a vector, say x1, x2, x3, and say there are d dimensions. This is a d-dimensional vector, right? And when I say what is the p norm of x, so that is basically so we are taking x1 to the power p plus x2 to the power p plus xd to the power p, and the sorry, 1 by 1 by pth root of this to the power p. So for example, suppose I'm taking x square. So this is basically square root of x1 square, x2 square plus xd square, xd square whole square, which basically, because the square root and this cancel out, we are basically x1 square, x2 square plus xd square. So this is your L2 norm. So what will be the L1 norm in that case? Anyone? So you understand this L2 norm, right? The definition of L2 norm. Okay, so what is the L1 norm?
So
If
is
you
there
look at
any
this,
L3 norm also?
yeah, so this P can be anything. P can be anything greater than 0.
Okay.
So there can,
So I understand P written above is the power that many times, but what is the meaning of P below?
this 1 by P. Oh, this 1 by P is basically your root. So suppose I write 4 to the power half. That means basically I
Okay,
am
the
writing square root
okay.
of 4. Yeah. So if I write 1 by 3, that is cube root of 4, and 1 by P is basically pth root of 4, something like this. So then what is the L1 norm? Yes,
x1
L1
plus
norm is,
x2 plus x3, etc. up to xd.
yeah, right. So this is basically the sum of these terms. Now, interestingly, what is the zero norm? L0 norm, if I say.
One, sir, is it one?
Uh-huh. So
One,
basically, you have x1 to the 0 plus x2 to the 0 plus
one.
x3 0. So this is 1, this is 1 plus 1 plus 1. So basically, if none of these x1, x2, x3 is a 0, so x0 norm is basically how many number of entries there are in your vector. What is the dimension of your vector? And another interesting thing is your L infinity norm. So this is not related. I'm just saying L infinity norm. What is this basically? X1 to the infinity plus x2 to the infinity plus xt to the power infinity. So let me give you an example. Suppose my x is 3, 4, 5. So my L2 norm is 3 square plus 4 square plus 5 square, right? My x3 norm is 3 cube plus 4 cube plus 5 cube. So basically this is 9, this is 16, this is 25. Yeah, this is 27, 64, 125. So if I increase this one 4, we have 3 to the 4, which is 81, 4 to the 4, which is 4 square into 4 square, 256, and this is, I don't know what, 625 maybe. So anyway, the point is that there will come a time when these things are growing very slowly. So this thing, you see, you have 25, 125, 625, and after that you have some thing in the thousands and 10,000s. So because the 5 is large here, so as we increase this p, this larger quantity will grow very large, so it will dominate the others, right? So basically, so then L infinity norm is basically defined as L infinity to infinity. It is basically defined as the maximum out of all the uh, coordinates of x. So this is not required. I'm just giving this as a side thing. So yeah. Anyway, going back to regularization. L2 regularization. So suppose I give you, so till now we are looking at losses of this sort, right? We have some loss, say the mean squared loss or something like that. Suppose, for example, in your regression, this is a prediction, this is a true function, something this sort. So now if I ask you to minimize over the set of parameters W, L of W plus half times the 2 norm of W. So if we want to minimize these quantities, so earlier whenever we're talking or whenever we're looking at unregularized losses, we are just saying that we want to minimize W with respect to LW, right? And we are able to, so this is basically you apply gradient descent, you just want to have an access to the gradient of this loss, and then you are able to straightforward do a straightforward calculus and come to the minimum. But now I want to minimize this whole quantity. So notice that we have a plus here, right? So since we have a plus here, this whole quantity will be minimized and this thing is minimized as well as this thing is minimized. So if you have something like this thing is minimized but this thing is high, this whole quantity will still be large. So we don't want that. We want both of these to be minimized. Right? Now, so we know that how we can. So suppose this is a mean squared error loss. We know the minimum can be computed using simple calculus. So now let us see what happens to this quantity. So suppose my weight factor is basically W1 to WT, right? And my L2 norm of W is basically W1 square plus W2 square plus WD square. Now, if I want this thing to be small, I want this thing to be small. What do you think? So this if this was small, these things should be small, right? This whole summation should be small. So because these are square terms, each of these is a positive number. So that means each of these wi's must be small, right? Each of W1 square, W2 square, WD square must be small. So this much is clear, right? Okay. So now as an example, what is 0.2 square? Anyone?
0.004.
0.04. Just
Zero
put this.
zero. Oh.
No, 10.
Okay, sir.
Huh. So if I say what is 0.02, then there will be 4 points after decimal, 0.00. So you see, if my W1 is less than 1, right, then W1 square is less than W1, right? And now if I want this quantity to be small, we want these quantities to be small, right? So whenever we are trying to minimize a quantity like this, we are trying to minimize a quantity like this, it will force my weight to be very small. It will force my, actually there is a parameter here as well. So it controls how strong it is. It will force my weights to be very small. So if my weights are very small, that means we are not trying to give very I mean we don't want to give large importance to some features. We're saying that we are giving small importance to each of these features. We're not say we're not giving a complicated model. We're just trying to learn a simple model. Why I'm saying that we want to learn a simple model? That is because we are not saying that the weights are large. We want our weights to be small. We want our model to be simple. So this is the effect of regularization. So it helps us to get to simpler models, and by simpler, because we want simpler models, because simpler models do not uh, overfit. Simpler models are good for it gives us good test losses, good validation losses. So yeah, this why we do regularization, and what is L2 regularization, what happens due to regularization. So these 3 points are clear, right?
Yes, sir.
Yeah, good. So in the class, a lot of regularization tricks are discussed. So this is a basic regularization technique. So basically, if you are using, I think PyTorch. So if you have looked at the someone's code or have coded, you will, whenever you are deciding an optimizer, whether you want to use ADAM, ADA RMS, or whatever. So there is an option called weight decay. So this weight decay is basically this lambda parameter, and it basically enforces our L2 regularization over your optimization, over your optimizer. So if at any time you require to code it up, this might be helpful for implementing regularization. So this is one type of regularization. Another thing that was discussed
In
in
L2, in the lecture, they are talking about some rotation, scaling, and again rotation. How is it related here?
okay. So the rotation, so there are two rotation things that were discussed. One was in the context of data augmentation, and another one was when they were looking at this age matrix, right? So basically, if you go and look at the derivations, so they get something like so I don't have the derivation exactly now, but something like you multiply your matrix H uh, with the difference of your weight and the optimal weight. So because H is a positive, in the last class we discussed that if something is a good matrix, say positive, symmetric, and definite matrix or semi-definite matrix, then we have a eigenvalue decomposition of H, eigenvalue decomposition of H. So that means H the so I can write H as some Q lambda Q transpose, where these are the eigenvectors of H, Q1, Q2, Qn. These are the eigenvectors of H, and these are orthogonal to each other. Qi is orthogonal to Qj. That means Qi transpose Qj equal to 0 for I not equal to 0. So basically, these eigenvectors are all independent. So you have some eigenvector Q1 here, another is perpendicular to it, this is Q2, another is perpendicular to it, say Q3, and so on. So we want this type of quantity. So whenever you are multiplying anything with a matrix, so I have some matrix X, I multiply with some A, so that means you are just rotating the vector X according to A. So in the lectures that they show, so they have this diagram, right? If you have gone through the lectures. So for the loss curve for my unregularized objective is something like this. And once I have the regularization, so we have something like this. And because I am doing a regularization, the weight factor that I get is something like this instead of this one. So if there was no regularization, we will get an weight factor something like this. But instead, we're getting a weight vector something like this. So in this case, you see the suppose you have two weights W1 and W2. So that means W is equal to W1, W2. So here, both of these weights are given the same importance, right? But here you see this weight is much smaller than these weights are much smaller, right? So because you are doing an L2 regression, so what did you see here? If you are doing an L2 regression, we want this W1 and W2 to be small, and that is what we are getting. Your W1 is small and your W2 is small. And how we get this vector is what is described by this matrix vector multiplication, which are basically rotations and scaling. Scaling happens because of this diagonal matrix, and rotation happens because of this Q matrix. Uh, am I able to clear your doubts? So you have to go back to the lecture and look at the derivations carefully again, but this is what it says, that if you do regularization, the magnitudes of these weights are reduced, and mathematically it can be shown that you are basically rotating the vector, weight vector, you are scaling the weight vector. Uh, are there any more doubts regarding this?
So
Okay.
there is scaling, or like the original vector has become smaller, but why are we seeing rotation? That is still not clear.
Okay. So a simple example, let me suppose you have x 1 2 and we have say 3 4 5 6, and then suppose I do a times x, say 3 4, this, right? So what will be the first quantity? 3 plus 8, 3 plus 8 is 11, and then we have 5 plus 12 is 17, right? So now this was my vector x, right, which is 1 2, and after I multiply it with x, what happens? You get to something like, so this is 11 and this is 70, and we get to something like this. So originally it was something like this. Now not this. So we have 1 2 1 2, and we have 11 70. So whenever you are multiplying a vector with a matrix, like I'm multiplying x with a, you rotate your, so you see this was the original x, this is your ax, so there is a rotation in this direction, right? Do you see that? So matrix vector multiplication is basically you are taking a vector and you are rotating it into some new coordinate which is defined by this type of by the coordinates of this matrix A. So the rotation, so is this example clear?
Yes, this is clear.
Hmm. So for example, if A is say the identity matrix and I multiply x here, so because this is identity, I get back the same x, so that means there is no rotation because this A matrix is the identity matrix. But if there is some other matrix instead of the identity matrix, we have some rotation. So the effect of this computation, the derivations that is shown in the lectures, the effect is uh, you have, if you have something like hx, so first of all you are just rotating x with respect to q transpose, then you are scaling it, and then you are rotating it again. So why are you scaling it? Because if I have some, suppose my lambda is say a 0 0, not a 2 and 3, and you have some say 1 2. So what is this? Basically 2 and 6. So this 2 6 is basically a scaled version of 1 2, right? So this is your 1 2, and we are scaling it by this matrix lambda, which is this one. So you're basically this is your 2 6. There is no rotation with a, because it is a diagonal matrix, you don't have any rotation, but you're just increasing the size of the vector. In some sense you're just scaling the vector. So this thing is clear, right? Rotation, scaling.
So if it's any other matrix which is not identical or diagonal, then there
No.
will be rotation also.
Yeah, so there will be rotation, there will be scaling, but if it is just a diagonal matrix, there is only scaling. So because you're just
And then,
uh,
and
uh-huh,
then, so first there is rotation, then there is scaling. Then why is there rotation the second time after scaling?
uh, so that if you have something like this, right? So first of all, you will multiply x with this matrix q transpose. So that is a rotation, right? So now let us say that q transpose x is some y, right? So now next, what are you doing? You're doing lambda times y. So this is a rotation, right? You're doing lambda times y. So you get something, say y hat. So because lambda is a diagonal matrix, so this is just scaling, right? Now what are you doing? You have this, so you have y hat, and then again you are multiplying with q. So this is again a rotation, right? You'll get something like y dash. So these
Okay,
are the
understood.
three. You get this, right? So it become these operations are applied one after the other from the right hand side. So that is a there, first there's rotation, then scaling, then again rotation, and these operations ensures that your weight vectors are the norms of the weight vectors are smaller than that of an unregularized version. Okay. So another concept that was discussed briefly in the class was data augmentation. So the way I like to think about these concepts of bias, variance, regularization is, suppose uh, so all of you must, of course, all of you have given your board exam, right? Class 11 or class 12. So if you are only looking at only one textbook, so there is a high probability that the paper that comes in the final board exam, it will contain questions which may not be in the textbook that you are given, right? So so the problem is that if you memorize everything in your textbook without even understanding anything, you will get into troubles when you are attempting your final board exam, because you have not understood the concept, you have just memorized everything. So that means you have not looked at enough examples. So that is why what we do for board exam is we go through different test series, we look at different type of reference books. So what we're trying to do is we're increasing the type of examples that you're seeing. So suppose say talking about physics, say, uh, so everyone must have heard about the H.E. Verma's book. So even if you go through all the examples of your school textbook, so I think most of us must have gone through the problems of H.E. Verma, because they give us different examples to look at. So why is that helpful? Then it helps us to create a concept, right? Uh, so look, if I look at only a certain type of problems, will not be able to generalize our concepts to questions that are not within that concept. So we try to look at different variety of problems, so that we get the overall view. So that is a similar thing that happens with data augmentation. So suppose you're looking at an image of a monkey. So a monkey is something like this, right? And now if you look at only a special type of monkey, uh, I don't know, golden langurs maybe, and someone shows you a picture of a gorilla or something, or not you, I mean, if someone shows a picture of a gorilla to the machine learning model, it will not be able to recognize it, right? Because it just understands that the langur has white fur and it has a black face and something like that. But a gorilla will have a black face, it has its fur is also black, but it is still a monkey for practical purposes. So what we try to show the model is that no, you just you don't just look at the color of the fur or this, you also have to look at the shape of the face, right? Like for the how do you define a monkey? You have two eyes on the front and you have some jaw like this and you have 2 ears, right? So how do you do that? So given an image of a monkey, I'll say that okay, let me just uh, let me just uh, keep the eyes. So I will crop out these eyes and suppose I pass only the eyes as an input. I just crop out these eyes and pass it as an input. Or sometimes I want to show that I want to give only the shape of the face. So I will blur this image. So if I blur this image, it will just have some sort of a round type of shape, right? Or if I want to say give you only the if I don't want my model to learn only about white furred langurs, I will just say that let me add some noise to the color of the fur. So earlier we have white fur, and now if on adding some noise, you will have some example which say colorful furs, right? So when I give these as inputs to the model, it will learn that no, we just don't want a monkey which has white fur and a black face as a. We don't want to recognize that as a monkey. We'll also the network will also try to learn by looking at the eyes. It will try to learn by looking at the shape of the face. It will try to learn by looking at the texture of the fur. So it will be more robust, right? So because it is able to look at different examples or different types of examples from the same image. So basically, if you have say 10 images of monkey, and so here for each image I'm creating 10 augmented data, so you'll have say 30 examples to look at, right? So you will have these normal images of monkey, you will have the eyes of monkeys, you'll have these colors, you have these furs of monkey. So you are getting to look at more data, or the model is getting to look at more data. It is getting to look at a variety of data instead of just the same type of data. So then the model will try to generalize better. By generalize, I mean, given a test example, it will there's a high probability that it will be able to say, okay, this has such features, so this must be a monkey. So this is also a type of regularization, right? Because you don't want to overfit to these features. You don't want to overfit to the feature that our monkey has only white furs. We just want to learn a general concept that it has some furs of this type. We don't want to overfit to the feature that it has a black face, because some monkeys will may have red faces. So it has, because of data augmentation, you are looking at the same image in from a different aspect, and so you will learn a more general concept about the image rather than say a simple or the same type of image. So this is again a type of regularization. So this is just an empirical trick that mostly people from computer vision uses. Uh, so this is clear, right? What is data augmentation? How, why is it beneficial?
Yes, sir.
Hmm. So it may not always be beneficial. Say, suppose you are looking at some MRI photos, you don't want to change the location of some disease, right? So their data augmentation will not be helpful, because if the actual image is showing that there's a disease present at a particular cell and you augment it, it will show you a disease at a different cell, then we have problem. But in general, for these harmless type of applications, uh, this data augmentation is helpful. Okay. So another thing that was shown was this concept of ensembles. Hmm. So by ensembles, I mean that suppose, so think of it like this: there is something happening in the country. So, so I, what happens in the country? Yeah, some bad thing is happening in the country, and you want a solution, right? So, is it okay for just one person to think about it, or is it okay for lots of different experts to think about it? It's better if, say, something is happening to the economy, so it's good if you have, say, 10 economists who are discussing together instead of just a single economist making the decision, right? Because you have lot of expert knowledge, and you can take a combination of all this knowledge to get a good knowledge. So this is basically the idea of ensembles. You train various machine learning models. So you have some model M1, you have some model M2, you have some model M3. So model M1 will say that the function it learns is say F1 hat. Model 2 learns some function F2 hat. Model 3 learns some function F3 hat. And then you combine this. Your final model is basically F1 hat plus F2 hat plus F3 hat, and say the average of this. So this is your final output. So because you have input from various experts, your output is much better than a single out saying than the output from a single model, right? So this is the basic idea behind ensembles. So this idea is clear, right? What the concept of ensembles? Okay. So in neural networks, how do you how do we look at ensembles? So the problem with neural networks is that the number of parameters are huge, the billions of parameters. We cannot just train 100 neural networks each with some billions of parameters. Nobody may have that type of compute power or memory for that thing. So what we do is, given a neural network, so you are given this neural network, suppose something like this. So you random with some probability you randomly drop some neurons. You cannot drop an output. No, you randomly drop some neurons. So if I drop these neurons, right? So you have some neural network which is something like this. See this. Right. Now for a second example, suppose I keep these neurons. For a second example, I keep these neurons. And I drop some other neurons. Better to draw it again. So now suppose I drop this and drop this. Now my network looks something like this. So these two are from the same network, same parent network, but due to this dropout thing that we are doing, but actually it seems like we're training two different networks, right? So this is a different network and this is a different network. So that means on the same data we are training two different types of models. So this is basically same as saying that you have three different models and you're aggregating the output of all of these models. So this dropout regularization is a form of ensemble training in neural networks. So, so is this clear? Okay, so yeah, so I guess this covers uh, almost all the topics that are covered in this week. So, are there any more doubts that you want to discuss?
So ensemble bagging is good or dropout is better?
So there is no good or better. So basically, you want to incorporate the knowledge of different models, right? So dropout is usually used for neural networks, and on bagging is used for others, say decision tree, random forest, or SVMs. So those techniques are used for different types of models. So you cannot say which one is better than which, but the core idea behind these models remains same, that you want to incorporate the functions learned by different functions, different models, and then you want to aggregate these things together.
So you said like bagging is computationally expensive, so uh, it's not used for neural networks.
Yes, because neural networks have a lot of, so these practical neural networks. So whenever we discuss this big neural networks, say, so suppose it's Chat GPT. So training Chat GPT once has taken around, I think, 1 year or so. So if you want to test 100 such models, uh, and if you want to do those in parallel, you can imagine how much time it will take. Of course, you can run this in parallel with high powered machine, but suppose a student will not be able to do that, right? So it becomes impractical after for large models. So we incorporate this ensemble within in the one training loop. So that is why we use this dropout type of regularization. We, with some probability, we toss a coin. Say if it is heads, we say that that neuron is not present in this training loop, and otherwise it is present. So this gives rise to a lot of it. There is a illusion of lot of say different neural network architectures. Is that clear?
Yes.
Yes, sir. Okay.
So I wanted to know like basic concepts like linear regression, multiple regression, and polynomial regression, like just a brief idea of those.
Okay, so I can just give a brief overview. So linear regression basically says that you have some points, right? And you want to learn some function. So linear regression says that the true function is something like a straight line. So suppose this is a true function. So this is a line, right? And we know the equation of a line is y equal to mx plus some c. So basically then we say that our model is of the form wx plus c, and we want to learn is w and c as the parameters. So this is basically linear regression. So for polynomial regression, we so suppose we have two parameters. So this only has one feature x, and this is the output level y. Suppose
And multiple regression has multiple features.
multiple regression will have multiple outputs. Say how do you say? So it may be that suppose you want to suppose something like this. Given some x, your output is what is the probability of x being, say, I don't know, blue, and probability of x being a square. So based on the input you want to, so here you're just saying that given some x, say what is the price of x. So this is a simple thing. But now suppose instead of a single output, you want to uh, predict a set of outputs, like probability of it being blue, probability of it being a square, and so on. So if y is not here y is one dimensional. If y is not one dimensional, so that means it is a multilinear regression. Clear? And by polynomial regression, we mean that suppose there are more than one features. Suppose we have feature x1 and feature x2, and we're saying that we're looking at 2-degree polynomials. So our feature is changed to x1 square, x2 square plus 2x1, x2. So now we are not just looking at x1 and x2. We'll have some weight with respect to x1 square, some weight with this, and some weight with this. So this is a polynomial regression. So these are very brief idea. I'm not able to go into
So,
details now.
so in polynomial, like it becomes a complex thing. I
Huh.
mean,
It becomes a complex thing. So because you're looking at different combinations of the this one
okay.
features, it becomes a bit complicated. So that is why
So
for higher
in
degree polynomial,
linear, in
uh,
linear, it's a straight line, and in
mhm.
polynomial, then it becomes curved.
You look at curves, yes. Right. Basically, that is the main.
And then multiple. So I was confused in this. Multiple means like features are multiple. Or like in
So
polynomial, also we are saying there are
Multiple
multiple.
outputs.
this is a multiple output, and these
In
are multiple features.
multiple features are there in polynomial.
So even linear regression can have multiple features,
Mhm.
but in polynomial we combine these features, right? X1 square, x2 square, x1, x2. But suppose your x is, suppose it is a three dimensional, suppose it has three features, right? And we are talking about linear regression, right? So then your W transpose X will be of this form: W1 X1 plus W2 X2 plus W3 X3. But your polynomial regression will be something like W1 X1, say power 2 square plus W2 X2 square plus W3 X3 square, W4 X1 X2, and all of these combinations. So linear regression is just a straight line, your slope into the point, and maybe plus some constant. But polynomial regression will try to look at all combinations of the features. So
And then
linear regression, uh,
multiple is somewhere in between.
multiple is basically so for linear regression, your y is a single scalar number. So y is just a real number. For multiple regression, your y is, say, something in RD. So suppose I say that, how do I say this? Mm, X1, X2. So this can also be a multiple linear regression where you are, each of these is a, you can think of each of these as an individual linear regression, right? One line for this, one line for this, and so on. So
Okay.
this has not been covered till now, but it is still useful. So basically, it linear regression has only one line for and one output. Multilinear regression has multiple outputs, and you have a one line for each output. That is, you are doing a linear regression for each of these outputs there is.
Okay. And then comes a logistic regression.
So logistic regression is basically the name is not correct. That is basically a classification type of thing. So basically, logistic comes from this logistic function. So suppose I say that everything here is class 0 and everything here is class 1. Suppose it is a binary classification problem and you have some sigmoid function like this, right? This is your sigmoid function. And suppose for some x, your output, so you have some x, your output is here. So you say that this x belongs to class 1, right? This is class 1. For some x, your output is, so x dash, you say that it belongs to class 0 because it is closer to class 0. So this is your logistic regression. So this is basically used for your uh, classification problem, binary classification problem.
Okay, thank you.
You understood this, right? So the regression just says that you are regressing to the probability values, but basically it is used for classification. But linear regression are used for regression problems, but this is for classification.
Okay, understood.
Okay, fine. So yeah, thank you for attending today's class. So we'll meet again next week, same time. Okay, bye bye.
Thank
Thank
you,
you.
sir.
Thank you.